So welcome to today's first lecture here to atmospheric chemistry and biogeochemistry. For those who are watching online, also hello to the outside world here. I hope our YouTube stream will work seamlessly today. It will be a test for everybody. Our idea is with these two groups that we announced through OLAT that every second week you have the chance to be physically here and have more interaction than just the YouTube live stream. If the YouTube live stream works seamlessly, you should also have an option to post questions through the chat online. There is some delay when we stream, so there'll be half a minute delay probably on average. And I'm also not always able to look at the chat instantaneously. I'll try to. So don't worry if I don't answer it immediately. I will keep it in mind. So that's just one additional part here that I would like to mention. The structure closely follows the textbook Atmospheric Chemistry and Global Change from Brasseur. We also have it in the library. So it's that book here. I'll show it to everybody. That's the main one this whole course follows. So that would be a good one. There's also, I think you can have it online, and I also have, if you do not have access to it, we can work on that. That's the one more specialized book. I think one that you might already know from Trento or otherwise is this book from Seinfeld and Bandis. I use this mostly when we talk about aerosols here. So that's another one. And for spectroscopy, upper atmosphere, radiative transfer, some aspects that we need. It's more a spectroscopy book, is the upper and lower atmosphere from Finlays and Pitts. So these are the main three books, even though I say the one, Atmospheric and Global Change, is the main one. And the individual chapters also follow that book. So that's in addition. Yeah, so what do we want to learn here? I guess it's pretty obvious. We want to know, have an in-depth view on atmospheric chemistry, some of the emerging topics, some of the well-established topics on atmospheric chemistry. Mostly our focus will be on the troposphere, but we'll also talk a little bit, of course, about stratospheric chemistry, which mostly relates to the ozone formation in the stratosphere, something you all probably heard already about. So we'll probably keep this quite short and then mostly focus on the chemistry of the troposphere. There's some things that are kind of required a little bit as a prerequisite here, and that is radiation interactions with matter. In our normal course of atmospheric sciences, there are several classes on radiative transfer in the UV. We would need that to understand a little bit photochemistry, and so that's a little bit of a prerequisite, but we'll have a very short excursion to that too. And in parallel this semester also you guys will attend another lecture where they will talk more about that. I think this is the radiation classes they will be visiting. So there will be some overlap, but this is also why I keep this rather short here. So as said, there's 8 core chapters, and we try to cover one chapter every Thursday and be done with most of our theory here before Christmas. That's the hope here. And so here are the individual chapters again listed. Today I'll just have an introduction here. Today and next week, or next session, a little bit of photochemistry. That's a little bit of a recap from radiative transfer and photochemistry in the atmosphere that we'll also probably hear in the other classes. Chapter 3 is essential one, atmospheric kinetics. Then chapter 4, we talk about reactive nitrogen in the atmosphere, the nitrogen cycle. Same for reactive carbon. These are three important chapters that we need to cover before we go then into ozone formation, which is closely linked to reactive nitrogen and reactive carbon in the lower atmosphere. Then we have this one programming exercise, a little bit, you could call it programming or data simulation exercise with quite a comprehensive tropospheric chemistry mechanism where we are trying to simulate ozone chemistry depending on initial conditions. So that's that here. Then the other chapters relate more to biogeochemistry. Again, the main one here for you to focus in, and I'll talk about this already today quite a bit, is chapter 8, aerosols in the atmosphere, which are of course fundamentally important to the atmospheric sciences. But then if you have time, we'll also cover a little bit these other two chapters. Exercise 2 will not happen this year. Rather, we'll just focus on exercise 3, which is part of, where did I have it? Yeah, using the master chemical mechanism in conjunction with some of the lecture material that I provide. So that's, that's that. So we'll start with the introduction. I think this is mostly basic stuff that you do know, but just to get everybody in the same board here, I think it's good to cover a little bit of that. So why do we study the atmosphere? Well, if you look at the planet as a whole, you could think the atmosphere compartment is really not so important. It's a very small reservoir. Well, this could maybe be true if you were living in the ocean, but since we are living on land, this compartment is one of the fundamentally important one to sustain life as we know it on our planet. The atmosphere itself is a very fragile layer of gas in the atmosphere that due to the gravitational force of our planet has not evaporated yet. If we compressed the whole atmosphere to 1 atmosphere, so that's standard pressure, what we have on the ground, it would be a gas ball with a diameter of about 2,000 kilometers. The mass itself would be about 5,000 trillion tons. Sounds a lot, but if you compare it to the other compartments of the Earth, the volume would be just 3% of the whole planet, so a very low volume. The mass even less. And so why I'm showing this? Well, what does that tell you? Any change or any environmental change in our planet mostly or manifests itself the fastest in the atmosphere because it's the smallest compartment, followed by the oceans and then the rest of the planet. So we can detect actually changes quite rapidly in the atmosphere as we do nowadays. For example, we see increasing temperatures much faster or quite a bit faster in the atmosphere, for example, in the oceans. On the other hand, in the 80s, for example, there's very fundamental research done on the ozone, stratospheric ozone, seeing that very small amounts of hydrofluorocarbon compounds can influence the composition of the atmosphere. And so that's why you have to keep this in mind. It's mostly the small reservoir and a very fragile gas layer that surrounds our planet. Now, how do we distinguish different layers in the atmosphere? Also, not something new here. The planetary boundary layer is the lowest part of the troposphere, where we typically say that's the layer where the weather happens. That's the most important component for weather forecasting. But then extending to about 50 kilometers, we have the stratosphere, and above that we have the ionosphere. So this is more a thermodynamical distribution or description of the atmosphere, different layers thermodynamically. We can distinguish the troposphere and stratosphere quite well because of the temperature inversion at the top of the troposphere. Question, why is it what causes actually the temperature inversion at the top of the troposphere? Is there any idea? So when we look So when we look at our atmosphere, we look at the temperature profile. Very roughly speaking, we see the temperature goes down and goes up and then down again. So this is temperature, and this would be height, where we say this is kind of the end of the troposphere. So this region often is called the upper troposphere, lower stratosphere region. And then the temperature seems to increase here. So the question is actually why?
Interaction between radiation and ozone, oxygen, nitrogen.
So when we follow here, I mean, there must be a process that heats the atmosphere, otherwise temperature wouldn't increase, yeah. And so, yeah, it was here getting in the right direction, but there's one very fundamental process going on here that causes the heating in the stratosphere. So I have one comment online.
Of the stratosphere?
Yeah. Yes, so here we are in the stratosphere. So we have the answer online. It's ozone, and it relates very much to this lecture. So the formation of ozone releases enough heat that you convert UV radiation to pretty much heat, and that causes the temperature to increase in the atmosphere. So that's actually part of this lecture, the explanation why we have a stratosphere. If there wasn't this mechanism of ozone formation, we probably wouldn't have a stratosphere as is, unless there was some other process, including some other process that would cause some energy input into that layer. The last layer here would be the ionosphere, extending up to 350 kilometers. We know this also from everyday applications. Radio propagation, radio waves needs the ionosphere because here we have charged particles. There's ion molecule reactions in that layer and free electrons that make this to some extent a conductive layer. Yeah, again, so most of the topic of this lecture here will be the lower atmosphere. I guess this is a little bit self-explanatory, this slide. What I just want to say here is, if you look at the Earth's history, the assemblage of the planet hasn't changed much on an elemental basis. So the number of atoms, carbon atoms, oxygen atoms, hasn't changed much. But what has changed fundamentally is the composition of molecules made of these elements. And so that, in that sense, our planet was shear transformed by life. That's why we have an atmosphere that doesn't exist on any other planet. But if you look at the elemental composition, it has stayed, as you would expect, fairly constant. But the important point is it's the atmospheric chemistry then, in conjunction with an oxidizing atmosphere, that really maintains the atmosphere as we know it, and has maintained it for more than 3 billion years now. Now, I have talked about the thermodynamic description of the atmosphere. This is again a more accurate drawing. So we have a temperature profile with the stratosphere heating due to ozone. Again, a temperature inversion here, and then the thermosphere here. What you also see here is the electron density. So you have ion molecule reactions. So the radiation up there is so hard that it really not just splits molecules apart, it also can ionize the air up here. So you have the F, E, and D region. And so from a more of an atmospheric chemist point of view, you could simplify the picture and actually say we have actually two chemical compartments that are quite distinct. And this is another distinction that has been made in the past. We can divide the atmosphere chemically and call everything up higher than 100 kilometers the ionosphere, and everything below here the chemosphere. Why is that, or what does that tell you? Well, what they mean about this is down here you only have mostly reactions of radicals and molecules, and do not have a lot of reactions going on with charged particles. Up here, as the name says here, you have quite complicated ion molecule reaction chemistry going on. So you have actually charged particles up here much more than would matter down here. Yeah. So this shows now roughly the light absorption with the sun overhead. You already see there's a strong wavelength dependence of absorption in the atmosphere in that UV part of the region. Now, at the ground surface, most of this hard radiation has already been filtered out by the upper atmosphere. So the ultra-hard radiation here, up here you can even dissociate nitrogen compounds, which would not happen lower, but on top of that there's enough energy when radiation interacts with the molecules up there that you start ionizing them. As you go down to the stratosphere, then most of this stuff then is filtered out by the composition of the stratosphere. So that's also pretty straightforward, I guess, just as a little overview. So again, one prerequisite that we require here is that we need to at least know basic chemistry. I think this is also something that needless to highlight here. This is, if you want to look up something, how many isotopes does a certain compound have. I like this online part of the periodic table. Now in the atmosphere, most of the elements present and that we need to worry about in this class would be hydrogen, carbon, nitrogen, oxygen, with some of the other trace elements. And so with just those 4 atoms, actually you already cover, I would say, 90% of the chemistry going on. Just the hydrogen, carbon, nitrogen, oxygen. Then there's a little bit of sulfur, and then more exotic elements that play a role in certain environments. So yeah, I think that's, also just as an overview, what is a nuclide, an isotope, an isobar, I think is also pretty clear here. So for example, if you look at the carbon atom here, the most dominant, the most common isotope would be the 12,6. We should know what the 12 means and what the 6. Hopefully, if not, go back and look at it. Now, the C13 isotope is about 1% roughly of C12. And then there's another one that's not listed here for carbon, which is a very common one used for dating, which would be the C14 isotope, which follows a radiative decay through beta decay. An isobar would be chemically different because it has a different number of protons in the nucleus, meaning it also must have a different number of electrons in the shells. And the electrons define the chemical nature of a molecule. So they have the same weight, but is actually a different element. So that would be an example of isobar. Now, if we plot all the elements that we know and plot them, see the number of protons versus the number of neutrons, we get a picture shown here, and the color coding shows us the lifetime of each compound. So roughly speaking, when it's in the red zone, it's pretty much considered a stable element. The lighter the color here, the more it means that it's unstable. What means unstable in that context? It's the weak force, atomic force. It will radiatively decay. One interesting thing, what you see here is there's 2 things. First of all, this is 1-to-1 line, and you see it curves up. So the more protons we have, the more charge in the nucleus, the proportionally even more neutrons you need to stabilize the core of an atom, that it's even stable. And even there you see the heavier you get, the more chance you have that the element is not stable. And if you look very closely, you see there's a certain number of protons, and above there, all the elements follow a radiative decay. And we can go back here. See here, where are we? Well, roughly everything heavier than Blei, lead, everything heavier is actually a radioactive isotope and will radioactively decay. It doesn't mean that we also have radionuclides here, but these are typically just isotopes of these elements. But everything heavier than 82, there is no single isotope there that would be considered completely stable. Again, how do we define molecular weight? There is the International Society of Chemistry defines 1 atomic weight, 1 Dalton. To honor Mr. Dalton, who was an American chemist, is like 12.011 grams per mole atomic mass. That's one way to define it. What you see often is what they call nominal mass, which is the rounded mass. So we say typically carbon has 12 grams. But what you see behind the comma here is very important. You can get additional information on the composition if you're able to measure it, for example. Especially with mass spectrometry, here you often can really measure the weight accurately enough that you can say which isobar you're measuring, for example, based on the exact number. There's also another definition here used in chemistry and mass spectrometry. Often, if you see that, the Kendrick mass is just defined as CH2. It's 14 AMUs, and that's again the exact mass. And so you can see where it's going. So then you can define a mass defect, which again would just indicate here what's back in the denominator. And the reason for that is, if you go back to our periodic table, and hopefully I can open this fast enough. So when we look at that, you will see that every element here has a slightly different weight from the nominal mass. So hydrogen is 1.008. Important for the atmosphere, since we are living in an oxidizing atmosphere, is oxygen. And so you see oxygen is actually slightly lighter. It's actually, you say it's 16, but actually it's 15.999. And from that mass defect, you can, with a mass spectrometer, for example, determine the exact molecular composition, or at least the isobaric formula from measurements. And that's widely used in analytic sciences, for example. So that's all so far concerning our definitions here. To give you an example now of what you can do if you're accurately measuring the mass defect, there is mass spectrometers out there. We have some instruments set up here at our urban air quality lab, which is in this building. Analytical lab with some mass spectrometers where we can measure the exchange of compounds that are emitted from the urban atmosphere and how they interact with the atmospheric chemistry. And so we have one expensive mass spectrometer here that is able to measure in situ composition of organic carbon compounds in the atmosphere, something that we will follow up later in chapter 4, if I'm not mistaken. We talk about organic carbon in the atmosphere. And so this is a typical snapshot of volatile organic compounds in the atmosphere of Innsbruck. Again, what you see here is the Kendrick mass effect versus the nominal mass here. And every dot here is representative of a mixed one molecule, or exactly speaking, one isobar. And so you can make these plots, for example, and then see that across the horizontal line here, you have chemically very similar compounds. So if you follow, for example, that line here, it will be the series of aromatic compounds that are very important for urban air quality. For example, benzene would be one of them, benzene or toluene. And as you can see, there's many different dots here. There's many different organic species, and something that will haunt us a little bit when we talk about the complexity of tropospheric chemistry. We have all these organics in the atmosphere that react, get oxidized, and then make something subsequently. Again, so this is just one measure, one example here, how we can determine the composition in the atmosphere. There's many analytical tools here. This technique has a particular advantage that it can measure very fast, and can also use it in combination with micrometeorological techniques such as the eddy covariance method. Yeah, so these are just some very fundamental settings here that I want to recap here before we really dive into more in our more detailed discussions. So a little bit of a historic view on air quality. Now, it's clear that air quality has been an issue for hundreds and hundreds of years. People have always wondered what defines the smell in the air, what's air quality. In the old days, it was mostly considered a local problem. Nowadays, we know that the atmosphere is a big chemical reactor and things get moved through transport through the air. So it's a very connected system also that connects transport and chemistry. And so it's saying here not just a local but a regional and even global phenomenon, depending on which process we want to look at. Oddly speaking, related again to infectious diseases, like in the old days, like in the Dark Ages when you had an outbreak of the plague, people always associated that with the bad smell. And so back then people thought that all these airborne pathogens are connected to bad smell, so bad air quality, and are transported airborne. So that was the very old view on disease, when people hardly knew what they were what it was all about, because there was a very limited scientific understanding. Where does the word smoke, smog come from? It's a combination of smoke and fog. And so I think our field, the atmospheric chemistry field and air quality field, really got jump-started throughout the industrialization here, with the important industrial nations here having some severe outbreaks of bad air quality. Here are some of the key events here that triggered air quality legislation. For example, you have the typical European smog type events during winter, high aerosol loadings. For example, in London there was 4,000 deaths in 1952 because of a stagnant weather situation and fog and smoke accumulating to levels where actually a lot of people would die. Same here in Donora, Pennsylvania in the US. Fewer deaths. Nevertheless, if you see the pictures, you thought you were in the middle of the night, while it was actually during day because there was so much soot in the air. So all of this led globally to the idea, or people realized that the air quality also has to be kind of regulated to some extent. And based on these events, then there's all these clean air quality legislation out there, starting really in the US and perhaps in Europe, that were exposed to these problems early on. So we have two types of smoke or smog events. I'm not sure if you already have heard about these two different regimes that very different but cause different air qualities. So we have the summertime smog and the wintertime smog. In Europe in the 50s, it was mostly recognized that wintertime pollution was really bad. On the other hand, in the US, especially in sunny California, it was realized in the 50s that there was another type of smog in the air during summer, when the air actually disperses pollutants more effectively than winter. So there had to be chemical reactions involved. That in that case, they found it's this haze, severe air pollution with severe ozone pollution. And so this is typical summertime haze, summertime smog, related to rather ozone pollution rather than these intense wintertime smoke or fog events. I guess that's also maybe important to mention here. Yeah, so what they saw, and this is really much also what we will talk about, this summertime chemical reactions sparked the field of atmospheric pollution research pretty much, that they realized you had nitrogen oxides in the air, and you shine light on it, and there must have been some other compounds they figured plus something else, and it makes a lot of ozone. And we know nowadays CO, but also a wide range of volatile organic compounds. They're emitted by combustion processes, but also plants. They have many different sources in our environment, and they will then in the end also contribute to the formation of ozone and other pollutants here in summertime. The wintertime phenomenon then is more related to acid rain. You have a lot of sulfuric acid, and that's usually co-emitted by coal burning. That's usually what you have in winter. In combination with stagnant conditions, then you create kind of this particle smog that has been triggering the European air quality legislation in the 50s a lot. So this acid rain thing here. It was important in the 80s. It's pretty much solved because power plants switched to clean coal, and they're able to remove a lot of the SO2, so that this problem was mitigated kind of in the end. That in Europe now, with the air quality legislation in place, you do have a lot of improvement in terms of ambient SO2 levels. Regional transport of pollution, that's also something that's a little bit of an emerging topic. So what they realize now, because in California and especially in the western US, they have very strict air policy legislation, for example, in national parks, where they want to have a pristine atmosphere, and they see now more and more that they cannot achieve this alone anymore by just regulating air quality in California or the western coasts in the US, because there's so much pollution imported from China through the west wind drift. And so they realize this is more like a global problem nowadays that needs to be also addressed in many ways in a global way. Yeah, and this is why it started all sorts of international activities to try to address air pollution more in a global context, as much as this is possible. And now China has a big pollution problem, and I think a lot of also the climate change legislation is more driven by chemistry and air pollution in China rather than trying to mitigate climate change. Just because they have a big air pollution problem to begin with, and people are realizing that in their everyday life. And that is maybe also a comment on the side. Now, the two major components in our air are what is our air made out of, mostly oxygen and nitrogen. Where is the oxygen coming from, we might ask? Why does our planet have oxygen? Is it just outgassing from volcanoes, or is there kind of an idea where the oxygen comes from in our atmosphere? Because if you compare our atmosphere on Earth with Mars and Venus, very different planets, most of the atmosphere there is CO2, so that's almost 90% CO2.
Yeah, because of photosynthesis.
Yeah, so that's biologically driven, invented by algae. And now also terrestrial plants, which make about 50% of oxygen is produced by plants on the land surface and 50% in the ocean through algae. So where is the nitrogen coming from? That's a little more dicey because we might often not have heard that. If you look on Mars or Venus, there's hardly any nitrogen either on these planets. So that's a little bit of a mystery too. So 80% of what we call air is molecular nitrogen. I guess there's not that many options out there. There is you can always say there's outgassing from the planet through volcanoes. There's other processes. We know it cannot be extraterrestrial input too much. So it also has to be somehow connected to biology. And it's actually bacteria and microorganisms in the soil, mostly responsible for reactive nitrogen. So all the nitrogen we have in the atmosphere is actually also because of biology. And we'll talk about this also in the nitrogen chapter a little more about. So that's to keep in mind. The main constituents of our atmosphere is actually made by biological processes. Yeah. Of course, the most important part was that algae first invented photosynthesis, producing oxygen. It's the first large mass extinction event, if you consider it that way, early on during the life of our planet, where all the microbes that were living in anaerobic conditions would die out because algae just started producing oxygen, accumulating in the atmosphere, and that all these other microorganisms couldn't survive anymore because they were based on the different conditions, different structure in the atmosphere. And so with oxygen now we're living in an oxidizing atmosphere, which is considered quite stable from a chemical point of view. Even though the atmosphere is never in equilibrium, chemically speaking, it's always kind of a shifting steady state. And connected to that, we also have water, of course, in the atmosphere, which is another important ingredient. And so water plus oxygen plus some radiation leads to a very important compound in the atmosphere. Without that, there would be no life either, as we know it, because the chemical stability of the atmosphere would be collapsing. And that's the OH radical, which is often called the detergent of the atmosphere. So I think this is fundamentally important compound also to this lecture here. OH is initiating almost every first step in the atmospheric oxidation, unless you would call the first step really UV radiation, of course, splitting something apart. But then the propagation and the cleaning of the atmosphere is caused by that radical here. And so that's a little bit of an outlook here. I think the next couple of slides are pretty self-explanatory. I don't need to go, I think, too much on water and air, so I'll jump ahead a little bit. This is also a little bit just to keep in mind when we define amounts of material in the atmosphere in that context of our lecture. We need to define kind of what do we mean by it. So the chemists define that by a concentration or a mixing ratio. And since the atmosphere is a gas ball with decreasing pressure as we go higher and higher, this is of course pressure and temperature dependent. So if we report mixing ratios or concentrations, we need to keep the ideal gas law in mind, which you need to use to convert different units from different from one framework to the other. For example, in air pollution, when you look at these data, ozone concentrations are all often reported as micrograms per cubic meter. For the kinetics people, they often report concentrations in molecules per cubic centimeter. These are both concentrations, just in different units. When you are in the remote sensing world, then you might discover that they talk about Dobson units, which is a column density of compounds. And then for us also very important here is we talk a lot about mixing ratios here, which the mixing ratio fundamentally defined is mole per mole. And so if you wanted to convert a mixing ratio to a concentration, you always need to go back to that ideal gas law, just as a heads up. Pressure, as we know, varies through height. And I think the next couple of slides are also just giving you an overview. I'll jump ahead a little bit today because I have something else here that I'll also in addition want to report a little bit. So we all know the scale height and all of these things. I guess pressure decreases with height, and of course this is also something to keep in mind when you report concentrations in different levels of the atmosphere. Nevertheless, I think I'll leave that. We also know what the lapse rate is. Now, again here, pressure and number density. What would be a number density? I already said it. So for the chemists, the atmospheric chemists, they talk about number density when you see a number like molecules per cubic centimeter. That would be typical number density. As opposed to mixing ratio, where for ozone, typically we would say here, when we have a typical ozone day in Innsbruck, we have 50 ppb parts per billion. So 1 billion would be 10 to the 9. So that's, I think, pretty self-explanatory. Keep watching over here to our CO2 sensor here. So now we are at 643 ppm. We know what the outside concentration is. It's 400 ppm. For indoor air quality, that's also a big emerging topic now, especially also within this pandemic here. There's some connections also to this lecture that I'll also lose a couple of words on as we go. Now I'm telling you already why we are monitoring that. So typically for indoor air quality, there is not a good marker to monitor virus load, for example, but it's a very good marker. We are all in here exhaling CO2, and there's some thresholds that are empirically determined that when CO2 concentrations go way beyond 1,000 ppm, it's time to open the windows. For many reasons, but this year, of course, that's also one measure. They are propagating more and more now to monitor kind of indoor air quality in context of the situation we are in. Yeah, so mixing ratio, I guess most of you heard of this. ppm, so for ambient CO2 concentrations in the atmosphere are nowadays around 400 ppm, parts per million. Most of the trace gases we will be talking about in this lecture are more in the ppb range. The OH radical itself is even lower, so that's in the ppq range. So that's really low concentrations in the atmosphere. So again, it's a list here. This is mixing ratios. If you're very picky now, you would say, well, these are not concentrations, but these are actually mixing ratios. How many molecules per cubic meter of a substance is equivalent to 1 ppb? You use Avogadro's number plus the ideal gas law to get the molar volume. The typical ballpark number for your molar volume at ambient temperature, standard pressure, is 24.4 liters. At 0 degree Celsius, it's the molar volume, it's 22.4 liters. So that's a very useful number to remember if you want to convert from units, one unit to the other. Again, here concentrations now, number density as a function of height. Pretty self-explanatory, I think. I'll skip that. Same with water. Water, of course, is present in much higher quantities in the atmosphere. We are definitely way above the ppm threshold, mixing threshold in the troposphere. Only when you get to the stratosphere, it gets very dry. So far, any questions? No, because then I will suggest we make a 15-minute break. The live stream will also continue and then resume. We open the windows, and then I'll move on to something else that I already touched a little bit on, aerosols and air quality. I think that's another little overview that I want to give right at the beginning of this lecture. And I think then we'll probably finish in time today. Okay? Thanks. So I guess we are all back here now. So the next part of this lecture course is maybe, because of the certain special circumstances, more about indoor air quality and aerosols. We will have, as I said already, a special lecture on aerosols. I would like to just briefly jump ahead a little bit here and define what we mean about aerosols. Most of you already have heard about it. It's very well established in atmospheric sciences here that aerosols are a fundamental component in the atmosphere. Without those, we wouldn't have clouds, for example. So it's defined as a stable suspension of solid or liquefied particles in the air. Similarly, we also can define hydrosols in water, for example. A hydrosol is a stable suspension in solid particles in water instead of air. So the air, the word itself already defines a little bit what we mean about it. Aerosol, something that's in the air. In air quality terms, what you see in air quality networks is often the distinction between PM 2.5 and PM 10. I also assume you have heard that before. Or is there any idea what these numbers stand for? PM means particulate matter. Well, it's already written here. Smaller than 2.5 micrometers. It has historical reasons. It's a typical ballpark number where I say you're in the accumulation mode still, and everything larger, PM10, starts being heavy enough that it falls out quite rapidly due to gravitational settling. From an air quality perspective, also the finer particles are considered more important. You can also distinguish between primary and secondary aerosols. In this lecture, we'll also talk a lot about secondary formation of aerosols. Typical primary sources are, for example, combustion aerosols, dust, or even sea spray. You can also have biological aerosols. So this just shows a typical image of typical aerosols that can be in the air. You can recognize what that kind of is. Sort of, well, actually not. If you look closer, they say it's about 1 micrometer, so that's a pollen, for example. It looks like the coronavirus. I'll get back to it in a minute. Typical pollen. This is, if I'm not mistaken, mineral dust grain. And that's here a typical aerosol particle from combustion. That's a soot aerosol particle. It's a black carbon soot. So there's a wide range. They go from nanometers to micrometers. Now we've talked a lot already about concentration for gases. And for gases, it's pretty straightforward. We have number density mixing ratio, or a classical definition of a concentration. For particles, it's a little bit more complicated because we can also count them. Or we can report them as a mass. So air quality networks typically report particle mass in micrograms per cubic meter. So you get one number for PM 2.5, but that number contains all sorts of different sizes of aerosols. And so when you make size distributed measurements of aerosols, often a number that's better suited is number density again. So how many particles per size per volume here. These are typical number densities here, because the mass is dominated by the larger particles. So it's not so representative actually for what's in the air, what kind of aerosol in there. You could have a lot of small aerosols, but the mass is still dominated by the larger ones. So that's just important to remember. And the reason why it's complicated is that we really go from nanometers to micrometers in diameter. So that's corresponding also the lifetime of aerosols in the atmosphere varies depending on size. And that's shown here now. Typical example for an aerosol size distribution in the atmosphere. And what we see here is back here we would have gas molecules, typical size. We are in the sub-nanometer range, in angstrom range here. And then here there's a interesting zone here starting from about 3 nanometers. We start talking about clusters. That's the beginning of the size where we would call something not a molecule anymore, but solid particles. So more than one molecule sticking together, forming in a particle. And really from 10 on here, it's pretty clear. So these are all aerosol sizes, aerosols. We have the Aitken mode, ultra fine particle mode. Aitken was a Swedish physicist who first talked about aerosols in the atmosphere. To acknowledge him, we call him Aitken mode. Important for atmospheric sciences is the accumulation mode here. As the name says, this is the size where aerosols have the longest residence time, from 100 to 1,000. These are also climate important, very important aerosol size for the climate issues, because these aerosols are the ones that float in the atmosphere and serve as cloud condensation nuclei. And again, you have the larger aerosols like pollen or dust in the PM10 range here. Now, that picture now illustrates a little bit why just reporting a mass, PM2.5 might not tell you all you want to know, because the mass of PM2.5 will mostly be dominated by those aerosols, and even a little bit from the coarse aerosols. So I think in scientific literature, it's typically what you see then people talk about is size distributions. So we'll talk about this in more detail. Now, by definition, most of the ultra small stuff is mostly secondary nature, because there's no primary process that produces so tiny aerosols. So these are the formation of aerosols in the atmosphere usually goes from the condensation of molecules on to these ICAM mode particles that then subsequently grow. Versus on that part of the size range, it's mostly primary sources that cause these aerosols. And in between, then you have a complex mixture of growth, transformation. So two aerosol particles can collide and stick together and grow, but the more common process is that organic gases can keep condensing on aerosols, and they grow by condensation. Just like a water droplet can grow by continuous addition of water vapor onto a water droplet or a liquid cloud droplet. So here are typical examples, again, to compare sizes of different particles. So here molecules are in the range of 1 nanometer, really not much above 3 nanometers, unless you're talking about biological proteins, which we are not talking about in this context. Here again, dust aerosol, colloids, and then this is something I want to dwell a little bit on that. So when we look at the size of a typical virus in the atmosphere, we are actually seeing that a virus is pretty small typically. So not much larger than 200, I would say 300 nanometers. These are really tiny organisms, as opposed to other organisms that are typically much, much larger. So aerosols are in the size of ultrafine particles, actually. So I think this is an old figure, though. I would say what we know now is typical size of a virus in the atmosphere, different strains. They go from 20 to about 300 nanometers. Again, just putting it in the context of atmospheric lifetime, so typically we can clump those sizes together and say this is the fine mode, accumulation mode, and coarse mode. And so this is, I think, where I want to stop a little bit now and talk about air pollution in context of aerosols and in context of this pandemic a little bit, why I think there is a quite strong connection here to this course too when we talk about aerosols in the atmosphere. So I want to switch here and talk a little bit about what we all are dealing with these days, and that's the pandemic. What is COVID? Of course, now we know it's a viral infection. And from the previous slides, what I showed you is actually virus is not so much different from a physics point of view than an ultrafine particle. And so it's a disease caused by the SARS-CoV-2 airborne, mostly, well, they're still debating whether it's an airborne or a droplet disease. I'm going to go into this a little bit. We all know from basic biology, I hope, what the difference between a virus and bacterium, for example, is. Is a hint. So what's the difference actually between a bacterial infection and a viral infection?
Bacterium has a nuclei inside, the virus not. The DNA is inside the nuclei of bacterium, and the virus has the DNA inside his shield. This is the difference between.
So both
so
have
DNA.
So both have DNA, yeah.
Yes. The virus needs to another organism to
replicate. Yeah.
To replicate, yes.
Yeah. So I think this is the essence for us non-biologists. I think it covers it pretty nicely. So a virus is kind of borderline between life. It's not self-sustaining life. It needs to infect another cell to be able to replicate. So it has the everything. It has all the information to replicate, but it doesn't have the enzymatic machinery. And so this is the main problem now, that the virus needs to infect something else in order to replicate itself. So it hijacks a cell or bacterium, for example. So that's the important difference. And this is also when we go back or think back of the previous slides on different sizes, why a virus is actually a very, very small particle or organism compared to a cell that's always much bigger, because the cell contains a lot of other machinery to actually manufacture things that sustain the cell, the life of the cell. And so that's, I think, the fundamental difference here that we need to be aware of. Now, how large is the virus? I already said it's about 30 to 300 nanometers. The current SARS-CoV-2 virus is about 120 nanometers in diameter. And so is there connections to atmospheric science as well? If you talk about hygiene, transmission rates of aerosols, and so on, there is some connection, and I'll get into this a little bit more in the next slides. Now, also a couple of comments, personal view. What did we learn so far? What are some issues, and what are some outstanding issues that are currently being debated in the medical community? Now, before I dig in, we all read these epidemiological numbers nowadays from newspapers so far, and Europe has a very kind of disconnect system now, where every country then reports numbers, and then there is some sanctions against countries that exceed some thresholds. The most important numbers that epidemiological studies or policymakers look at is the reproductive rate, R0. I think this is pretty clear nowadays. Or what does R0 mean? Well, this is how infectious is a disease on average. So how many people does one infected person infect? So if the reproductive rate is 2, for example, it means that one infected person on average over the population infects another 2 people. And then when you implement mitigations like wearing masks, social distancing, lockdowns, again on a statistical population average, you get RF, the effective number that is responsible for the infection. And so if we have a little group plot, because there's also some climate air quality questions related to that, because the lockdown caused an unusual intervention experiment that allows us to study the compositional change. But I want to just scroll down here. And here are some of the epidemiological numbers here for Austria. So this is now our effective reproduction rate in April, when the disease also started to be propagated, transmitted in Austria quite extensively. We have our R0 of around 2 to 3, and then with the lockdown it drops, and then we are in this phase, what they now call the dance phase, the hammer and the dance. I'm not sure if you heard about that article. If not, you can go to our homepage here, and it's the first link here that should work. Yeah, the hammer and the dance describes all the measures they're thinking about nowadays, and what to do and what not, and what is cause and consequence when you have intervention. You say, well, you close this or that. And so it's all targeted towards minimizing the exponential growth. And the exponential growth is pretty much determined by this number R. And so what you can see in Austria here, then you have a hard lockdown, similar to Italy. Eventually, it goes down quite rapidly. And then we are below 1. And when R is below 1, if you kept it below 1 for a long time, it would die out, because then on average, one person would affect less than one person. And so this is the hammer, what they say. You have a hard lockdown, and then the case finished for some time. But then, of course, the disease, it's a very successful virus. It will not go away anymore. We'll have to learn how to live with it. Then there is this, what they call the dancing around the number of 1. You want to keep it below 1, that this exponential growth will be inhibited. So this would go on until there's herd immunity in the population. And you can also calculate from this number roughly what that would need to be. In case of a reproductive factor of 2 to 3, you'd need to reach a herd immunity, in theory, on average, of about 70 to 80%, which is kind of the standard, I guess, idea about that concept now. Now, just think about it. This is just always, you have to think about it as a statistical ensemble average. Now, I assume that everybody here has heard about this R because it's reported always daily in all the newspapers. What we might not have heard too much is another important part of epidemiological numbers and epidemiological parameters here, and that's when we talk about the distribution. So it's not that every infected person infects 2 other ones when R is 2. It could mean that one person infects nobody, another person infects 10 people on a statistical basis. And so this is in statistics described by the shape of the distribution. And so now the epidemiologists talk about K as kind of a measure how skewed the distribution is. Similar than when you look at turbulence spectra, for example, you have skewness and kurtosis. It's the same here. What kind of distribution do they use to model outbreaks? It's the negative binomial distribution. And there's this shape factor K that defines another important property here. Again, so this is just one side of the story. They use the binomial distribution here to model the distribution here because it's a discrete event. One person infects 1 or 2, but then on average, of course, R can be somewhere in the range, in that case, between 2 and 3. That's a typical number here. On a average over the statistical distribution, of course, you could also have an R that's not discrete. But in reality, one person can only affect 1, 2, 3, 4 other people. And that's why the binomial distribution is here the one you want to use. Now, if you look at this and have a little MATLAB script to visualize that. So for SARS-CoV-2, R0 is between 2 and 3. So it means it's not super infectious because measles, for example, has an R factor of 10. It's really infectious. Here we are actually in the range of the influenza, which is also around 2, maybe a little lower. But the bigger difference, what you see is the K value here is 0.1 for SARS-CoV-2 and 1 for the influenza. It means that in both cases you have a skewness, but it's much larger for SARS-CoV-2. And so if we, oops, wrong one. So I implemented this MATLAB distribution just in these 2 cases. The next plot is constructed based on the binomial distribution. So X here means that would be our R value. And then on the vertical, we have the probability. And again, this is for SARS-CoV-2 and the typical HNN2 influenza virus that has a K value of 1. So on average, it means that I plot here the average by these vertical lines, that on average, if you assume that the influenza has 2.1 and then SARS-CoV R average of 2.4, if you did nothing, let's just assume that, you could say, well, there's not much difference between those two. But when you look at the distribution, actually, you see that the blue line here, it's just a linear scale and log scale, so it's the same curves here. You see that more than 72% here has a probability of 0, which means that 72% of the people do not infect anybody else. For the influenza here, it's lower. We are around 0.4, so about 40%, half the people, or even less. So it's not a super infectious disease like, as I said, measles. It's very effective. Now, what does that tell us on the other hand? So if 70% on average don't infect anybody, it means that the low number of people must infect a lot of people, that the average again is over here. And that's what we see here, that the blue curve levels out much later. And that's from an epidemiological point of view, strong indication for these super spreading events that are very characteristic for SARS-CoV-2. We have a lot of asymptomatic super spreaders and super spreading events where this is something that we know now or for a while that that's an issue. And so now the question comes, what causes these super spreading events and what's actually the transmission route, the dominant transmission of this particular virus? I should say here we talk mostly about respiratory viruses. There's other viruses that are transmitted through other processes, but if you talk about respiratory viruses, what does that mean? Now going back to aerosols a little bit, you can guess that a little bit. Now we have a picture of the coronavirus. So it's 120 nanometers in size. And it turns out that there has been quite some fundamental misunderstanding also in the medical community about transmission. And there's still an ongoing dispute in the scientific community now between actually atmospheric scientists and aerosol physicists and the medical doctors and the hygiene literature. Because it turns out there is a big misunderstanding still at the level of the WMO that there's a lot of evidence now that the spread of this disease is mostly airborne and not really the classical routes. Now again, coming back, here is the coronavirus, 120 nanometers. These spikes here are the key. These are enzymes, and our cells don't recognize, or they think it's something they can absorb. So these spikes open the gate to the cell, and then the virus is absorbed into a cell and can release the DNA and infect the cell. This is kind of biochemically how it works. But in terms of infection rate now, so we have something that's 120 nanometers in size. And mostly now, of course, everybody agrees that it's transmitted by either fomites, droplet transmission, or aerosol transmission. So these three routes, fomites, what does that stand for? This is in Deutsch, we say klassische Schmierinfektion. I'm sorry, I don't know the Italian word. But what they mean by it is you have a contaminated surface. Or like say I cough in my hand, which is something that we shouldn't do because we cough in the hand and shake somebody's hand and he touches his face, then he's infected. That would be the fomite route. Or I cough on the table and then somebody else touches it. And this is why they use these disinfectants. So this is the classical route. They can be effective for some virus transmission. Then there's the droplet transmission. The classical idea is I sneeze and you're in front of me and you get the droplets in your face. Or a cough and then you have the droplets in your face. And the last one is then the aerosol transmission. Now, so this document kind of summarizes this dispute now between different communities, because now the atmospheric scientists realize that the medical community has been a little bit on the wrong foot here, that these super spreading events can only be explained by airborne transmission, so meaning that the virus is transported some sort of aerosol through the atmosphere. So that's, I think, an important message here. And the WHO refused that. Even in March, here they say COVID-19 is not airborne. They still are kind of have doubts about that. So the WMO still would argue that droplet transmission is the major one. Everybody pretty much agrees that this route is a very minor one for SARS-CoV-2. It doesn't hurt when we disinfect hands. In fact, washing hands with soap is the most effective way anyway. You don't need an expensive chemical. The lipid layer of the virus is very susceptible to soap and it immediately breaks apart. Either way, people have worried a lot about disinfecting everything, and even though some news reports from Bolzano where they go through the streets and spray everything down is completely nonsense. because it didn't do anything. Here in Austria, they also think about some hygiene measures that are not very meaningful if you don't control the aerosol transmission. And so there is this dispute still going on, and I'm showing a couple of slides now, why and what some of the misunderstandings were in that context. Now again, on a picture here, classically, you have the droplet route would be the called ballistic trajectories of large droplets. So I sneeze at you, and if you're 2 meters above, the gravitational settling is fast enough of these droplets that they'll fall to the ground before they reach your face. Oops. And so this has been the argument, because there's evidence when we socially are distant, so distance works, and this has historically been the argument of the medical community, the hygiene literature. This is why it has to be droplet transmission, because the idea was that aerosols float in the air, and if it was just aerosols, it wouldn't really matter if you're 1 or 2 meters apart. Now this is one fundamental misunderstanding from the medical community, because obviously they do not know much about the atmosphere and atmospheric transport. Of course, the distance also works for aerosols, not because they settle to the ground so fast, but much more because they get diluted. And so the argument that distance of 2 meters is a good measure is not because you have all these droplets falling to the ground. It's more like the aerosol cloud can get diluted. So of course both can happen, but it doesn't preclude aerosol transmission. This has been one major argument from the medical community that has been kind of debunked a little bit. Again, the fomite route, everybody kind of agrees on that, is a little bit not so important. The second fundamental problem that the aerosol scientists that never looked at that either, just because nowadays it impacts every person on the planet, they started looking at all of this. They realized that the fundamental definition of droplet and aerosols is completely wrong in the hygiene in the medical literature. It dates back to a specific study 100 years ago from a doctor in the US, at least, from a doctor called Chapin, who was a very successful doctor and infectious disease expert. And 100 years ago, he made some strong arguments for a lot of infections, including some viruses. The aerosol route is not so important. And then they find, though, these limits here, where in atmospheric sciences we would say this is completely wrong, actually. Because in atmospheric sciences we have a very good understanding when you have an aerosol, water condensing on it, forming a cloud. And the real limit here would need to be 100 micrometer, so 2 orders of magnitude higher. And that is a major misunderstanding where people often get confused by droplet transmission versus aerosol transmission. Often they associate things rather with droplets rather than with aerosols. And so now some of the aerosol scientists would argue, and actually it's a growing number also of the medical community, also in the US, where this is now really at the top level, this argument going on for 6 months, that would agree now that this, you cannot neglect the aerosol transmission route anymore, which was until very recently. Now this is, I think, a basic take-home message here. So all the lifetime calculations are actually wrong for 5 micrometer particles, because these are not droplets, these are aerosols. And it's a little bit more than just the semantics part of the story here. It's kind of a fundamental realization nowadays that this thing needs to be kind of reworked a little bit and redefined. Yeah, so the first argument that was brought against aerosol transmission was the distance. This is, as I said, a no-brainer for an atmospheric scientist. We all know how a Gaussian Bloom model works. It's not much different here. So the aerosols, of course, get diluted as we go farther away from the person. There's also some interesting studies out there from engineering people and aerosol indoor air quality people that visualize actually aerosol production and transmission and transport, because now it turns out we have a very good understanding how these super spreading events work. We know that they cannot be explained by droplet transmission, But then how are these aerosols generated? Well, it turns out when we speak, breathe, we also always emit an aerosol distribution. This is visualized here in this recent paper. If I simulate this before I start, I should say, so what they do is, so the person speaking is on the right side. This is about 2 meters across and 1 meter vertically, and what they let the people do is say different sentences. In that case, he says, Peter Piper picked the peck. And then they, as the person speaks, they look at how this aerosol cloud disperses. And so what we see here is very effective aerosol production while we speak, even while we breathe. And these would be all aerosols that you wouldn't be able to see because they're just too small. They're visualized here by an imaging laser system. And what you also see is then, so he speaks these consonants, and then there's more and less, and we also know, they also know that the louder you speak, the more your aerosols you make, and then they get diluted. You also see the turbulent wakes here, just quite common as if we were to look at, for example, exhaust stack in the atmosphere, and you look at how that disperses. And so the distance works also because the farther away you get from the person, of course, the more they're diluted. But the other, even more important consequence of this misunderstanding is that dilution seems to work to mitigate that disease. And this is what you will see more and more in the months to come, that people will argue more and more about dilution in the indoor space. Number one. Number two, there's also strong evidence that there's not a lot of transmission outdoors where you have lots of turbulence always and lots of dispersion because of the lower atmosphere structure, the high Reynolds numbers there. It's also a very strong argument. These super spreading events always seem to happen indoors when there's a lot of people speaking loud, maybe singing, and you have this cloud of aerosols accumulating to a threshold that at one point is high enough to infect people around. So ventilation is the key essence here. Because with a simple argument that it's just droplets, you would say, well, ventilation is not so important. So this is why I think one needs to realize that this was a complete misunderstanding of the highest level of WHO. And if you want to go through the history of all this argument, you can go through the link that I posted here. It's from colleagues in the US who are experts in aerosol science. There's even be a National Academy meeting now where the top infectious doctor in the US, Dr. Fauci, now agrees now slowly also that airborne transmission might be a dominant one. And that could revolutionize also the hygiene measures because it's not far-fetched that maybe for influenza or any kind of cold virus, it's more like the aerosol route than the droplet route that causes the propagation of these particles. So there has been also case studies long ago on other airborne transmissions, TB, tuberculosis. It's a bacterial infection, but also highly infectious as airborne. And what they saw is they also got these super spreading events in indoor places, in that case in hospitals. And they realized it also had to do with dilution somehow. And so they realized when CO2 concentrations indoors were above 300 ppm, this is also a limit where indoor air quality policies would say you should open the windows or should vent because of other pollution that could reach levels that you don't want to be exposed to for a long time. But anyway, they saw 3,000 ppm, they started having these cluster outbreaks of TB, and then they started to really dilute and vent indoor air. They saw that increase in ventilation, 90-70% of decrease in the transmission rate, and they found that 600 ppm is kind of a rough, for that disease, a rough threshold where if you keep the ambient concentration of CO2 that accumulates because we exhale CO2, and CO2 is just a proxy here, of course, so it's not, has nothing to do with the virus, but it's a proxy here that you could use to say, well, if you stay below it, you're kind of in a green zone. So that's, I think, one message from that. Of course, for COVID, there's these data. It's too early to have these data, but tuberculosis is highly infectious also, so I think it's a good threshold. So I think, this is one way to think about it to mitigate airborne transmission. So this is also something that people on the stream cannot really follow maybe closely, but what we have in here, if you look at, let's see if I can just turn on the light here. We have a CO2 sensor here, and when we look at where we started before we left for the break, we had a CO2 concentration of 672 ppm. So I would say this is still acceptable. Then we opened the door and opened the windows especially. It dropped quite fast to 455 ppm. Outside concentrations are typically in the range of 400 ppm, so this is kind of really acceptable level. And if you look at the concentration now again, we are back at 6, what do we have, 656 ppm, and it's about another 45 minutes here. And so this is, I think, one very cheap and easy way how to kind of mitigate air quality in that sense, in the wider sense, indoor air quality, and prohibit excessive transmission of that virus. Now, one other argument has been, and I'm getting back a little bit to the virus itself. You saw that the diameter of the virus is very small, and one argument has often been, well, this is also not why masks are so effective for a virus, because the size is 100 nanometers, the pore size of your mask is much greater. There's two misconceptions about that. Again, if you look at the CDC, that's the American Center for Disease Control, how they picture this aerosol transmission as I speak. If you look at the cloud I showed you before, they think, well, you get the idea, well, you have one virus that's covered with a little bit of water, and that's part of the aerosol. Well, this is not what you see in what you have seen in the previous movie. When we go back here, this is not what you see here. So what actually happens is that when I speak here, you exhale aerosols that are much bigger, so they do not contain one or two virus particles in it. If you were infected, they contain many, many more. So this is also something that's well known in a specialized field. Let's see if we can go back to the blackboard again. Very well established here. When we speak and when you look at this aerosol cloud, what you actually exhale is also a size distribution. So let's say we have size here versus number density. Typical speech aerosol shows up like this, where the modal peak here typically is around 3 micrometer. And so you can now do the calculation yourself. You have a 3 micrometer, on average, the modal peak of 3 micrometers can contain a lot of, if somebody was infected, it could contain a lot of 100 nanometer aerosols. So it's more like you have these larger aerosols, and if you're infected, they can have, depending on the status of your disease, stage where you are and how high your infection is, contain quite a number of virus inside. What happens then, and this is maybe another important thing that people realize, is so we exhale that aerosol at our body temperature, which is about 37 degrees. It's very humid, just like a cloud, but at different thermodynamical conditions. So what happens next is that, especially if the room relative humidity indoors is below 50%, these aerosols lose a lot of water, so they shrink, and so the size distribution after some time maybe looks like this, that the peak here would be more at 1 micrometer. And so what does that mean from an atmospheric physics point of view? Well, the smaller in that range, we are in the accumulation mode, the smaller, the longer the lifetime, which makes it a little bit worse even, because the smaller you get in that size range, the longer it will dwell around. And so this is another measure why people argue, which is then hard in wintertime in our climate zones when we open the windows a lot to keep the humidity high. You say humidity above 50% prevents the rapid evaporation of water. Anyway, so that's a couple of words to that. Also, a last one. So now there's two reasons why masks are kind of effective. First of all, it's not that we exhale one virus at a time as a single particle. It's more like we exhale aerosol spectrum that contains a lot of this virus inside. And so the actual size that the mask would need to filter is also bigger. The other reason is also, it's just an overview. What's a surgical mask and what's an N95 respirator mask? This is just more airtight than the surgical mask, more effective. And there have been a lot of studies out there how efficient it is. And that's just shown in my last slide here. So when you look at the efficiency, how much does a mask filter from that aerosol, depending on size, again, particle diameter. So you see that it's very effective actually at ultra small particles. And it has to do with the diffusion. So this small particle diffuses in your mask and immediately at one point diffuses towards a fiber and gets absorbed. Then you have a little bit of a minimum, and then again at 1 micrometer you have a quite strong filtering efficiency. And the reason for that is that here you have diffusion, and then here you already have impaction interception. So let's say the aerosol directly collides with the fiber in your mask and then gets deposited there. Another important impact, and this is or effect, and this is also why actually these N95 specifically are also using that effect, is electrostatic attraction, which we all know maybe from school when you have a water flow and you rub like a plastic spoon to get some electric charge in it, and then you put it close to the water, you have electrostatic force and the water will bend a little bit. The same happens here, that aerosols, it turns out, are very prone to the electrostatic force. So when you have a plastic material, it really attracts aerosols when they go through electrostatic attraction. We have one example from a completely different observation. Again, I go back to our observations here in Innsbruck, where we have long Teflon lines to bring gases to our instruments from the top of a mast. So we suck air, outside air, all the way into our lab. And what you see here is, unfortunately, it's very faint here, but what you see is here a piece of Teflon tubing at the very end, where we expose the tube to outside air, and the air flows through here. And the diameter of that tube is about 6 millimeters, a quarter inch. And so for our CO2 and NOx measurements, we pull air through these lines, and we pull outside air through these lines. And what you see is in the first centimeter here, it's black, it's soot. So that's outside aerosol that's already deposited very close to the very beginning of our line. And this is a well-established effect. So if you measure aerosols in the outside air, you never use plastic or Teflon lines. And I should say we don't use these to measure aerosols. We use this just to measure gases, where the effect is less of a problem. When we measure aerosols, we typically use conductors like copper lines or stainless steel because of this electrostatic deposition and diffusion. And this is the main reason also why these masks work. And this is often forgotten about in this whole discussion about do masks work or not. There's some very hard physical evidence on all these things. I think that is just worth mentioning here. So yeah, with that, I guess I'm done for today so far. I hope something that you learned today also, going a little bit beyond this lecture today, this lecture on atmospheric chemistry. As you see, there is always some strong interdisciplinary links between different fields. In terms of this current pandemic, it becomes really obvious that the medical community lacks understanding of aerosol physics as the main transmission route, and this is why in the future I think there will be also more interdisciplinary communication going on, I think, as we go. One thing, my prediction here is what you will see is that because more and more people will accept the idea of aerosol transmission, what you will see is here mitigation of aerosol transmission in indoor spaces will become more important. Schools, for example, are very prone to infection and transmission, and so in Germany now people start talking already, equipping all schools with CO2 sensors to just keep the dilution down. So I think this is some emerging mitigation that I expect we will see in the coming